Hey, so this is that problem that I said that I would record a video. I guess I didn't say when. It is admittedly later than I wanted it, but let's jump right in. So we were talking about combustion products here and how you measure and calculate an empirical formula from those things when they're combusted by trapping them in something like an H2O absorber or a CO2 absorber. So we're looking at this problem here, and we have a 0.8009 gram sample of a compound containing only carbon, hydrogen, and oxygen, and that is important. Now, we know that it produces 1.6004 grams of CO2 and 0.6551 grams of H2O, or water. Find the empirical formula of the compound. So we know we're going to have a compound that has carbon, hydrogen, and oxygen in it. And you may be concerned at this point, well, how do we get the amount of oxygen? So CO2 and H2O both have oxygen in them, but that oxygen is coming from, at least in part, from the oxygen that's being flowed into the sample chamber. So oxygen being added to the furnace. And so we can't rely on the amounts of oxygen combined with the hydrogen or the water and the carbon dioxide to get that amount of oxygen. Now, unlike the previous problem here on slide 35, in this problem 35, we were not given the initial mass of the sample. We didn't need it there. Didn't need it there because we were only looking for carbon and hydrogen. But in this problem, we're looking for oxygen too. So we can figure out how much carbon and how much hydrogen are in our sample. And then once we know those masses, we can go back and say that any extra mass would have come from the oxygen. So if we look at this, we know that our total mass is 0.8009 grams. And we'll need that, but not right away. And then we could also say our 1.6004 grams of CO2, and we want to figure out the percent mass. So we want to figure out the percent mass of carbon and the percent mass of oxygen in this. So CO2 will have 12.01, that's grams per mole carbon. And we're going to have 16.00 grams per mole oxygen. So carbon, oxygen. We have one carbon, two oxygens. Kind of did this backwards. So that is going to be 44.04 grams per mole total. And then what we do is we assume that we have 1 mole of this compound. So in 1 mole of that compound, it would just be 44.04. I'll write this out. So that times 1 mole is going to be 44.04 grams. And then if we had 1 mole of that compound, we would have also 1 mole of our carbon in there, which would be 12.01 grams. And so whatever this is going to be our proportion of carbon. You could multiply that by 100 to get a percent. 12.01 divided by 44.04. So that means that carbon dioxide is 27.271 percent. So actually, I don't want percents. I want to put 0.27271, and that's that much of carbon. And actually, we could, and I'm going to do this for water, could just borrow some of this information from up top here. So for carbon dioxide, we'd already calculated that as that. Oh, sorry, this is not 44.04. This is 44.01. So this would come out to whatever number we got up top. So 0.27289. And then we know the proportion for water is going to be this one, right? 0.112097. 112097. And this is kind of the law of definite proportions. Every water sample will have this percent mass, or this proportion mass, of hydrogen. So now we're taking, for carbon, the 1.6004, we're going to multiply it by 0.27289. That's proportion of carbon. And that tells us how many grams of carbon. So that's 0.43673 grams of carbon. Now for the hydrogen in water, it's going to be 0.6551 grams of H2O, and we multiply that by our proportion for water. There's 0 of hydrogen in water, 112097. So 0.6551 times 0.112097 is going to be 0.07343 grams of hydrogen. And we're keeping really extra digits here. Actually, we might want to keep one more for hydrogen. Call that 347. Yeah. So with that in mind, now we can take our 0.43673 grams of carbon plus 0.0734347 grams of hydrogen, and that equals 0.510167901 grams of oxygen, grams of hydrogen and carbon together. I'm going to have to insert a slide here. Add page. One of the best things about technology. Okay, so we know that our compound, out of all of this mess, is this many grams of hydrogen and carbon. And our initial sample, I'll write it over here, is 0.8009 grams of oxygen. So if we subtract out the mass of the hydrogen and the carbon, that'll give us this is just the grams of the compound. So if we subtract out the mass of the hydrogen and the carbon from the mass of the compound, so 0.8001 or 8009 minus that whole long thing, then it's going to be 0.290732 grams of oxygen. And then we can take all of these numbers finally and calculate an empirical formula. .290732 grams of oxygen. So our first step here is we want to convert these into moles. So we'll use the molar masses, 1.01. And this is 16.00. And then, let's see if I can use all the exact numbers from my calculator. If you have the same calculator as me, storing these numbers is useful. So I'm going to store that one as X, so carbon, and then store this number as Y. And then store this number Z on my calculator. So this is 0.0363641. That's moles of carbon. And then the mass of the hydrogen divided by 1.01 is 0.0727076. Well, I guess I'm here, so I might as well write them all down. Moles of hydrogen. And then the mass of the oxygen divided by 16 equals 0.018170756. Again, writing out just really too many just to be safe. Okay, so now we look at these and we pick the smallest one, which is the moles of oxygen, and we divide everything by that. So that one's going to be 1. So there's 1 oxygen. And then this will be divided by that. So that divided by that. So this is 2.00, and then the hydrogen number of moles divided by the moles of oxygen. If I can do things correctly on my calculator, is 4.00. So this will be 1.00 exactly. Oxygen, hydrogen, carbon. So the empirical formula is C2H4O1. So I can leave that off. And that is how you solve that problem.